Double quadrature means, I'm going to perform IQ splitting 2 times. Down conversion, converting from RF to IF is called as down conversion. So in Hartley oscillator, we have seen the issues there when you are going to have uh, mismatch. So when the amplitude, frequency, phase are not perfectly matched, the image is not getting cancelled perfectly, right? So one way of reducing the mismatch is using double quadrature down conversion. So this will decompose your RF. This will decompose your RF signal into quadrature components. So and then again it will convert. It will work on each RF component again to quadrature down conversion. When you finally subtract and add, you will get the final quadrature IF outputs. So that is going to be the concept. I'm going to do IQ splitting 2 times. So see here, image rejection of first stage, image rejection of second stage. So when you do cascading, you can see the image rejection. And when this is going to be the magnitude of cascading. So at the desired frequency, you can see you have a peak amplitude. Otherwise, image rejection, you see at the at the filtering frequencies, the image value is going to be 0. Okay, so this is going to be the image rejection characteristics, and these will consider the gain and the phase mismatches. So delta A is going to be your gain, delta A LO is the gain of your local oscillator, delta A RF is the gain of your RF signal, and delta G mix is going to be the gain of your mixer. So when you consider the phase, this is the phase relation, this is going to be the gain relation. So the quantities will determine how much amount of mismatch you are going to have in the gain and phase. So we have seen in the previous case, the image rejection ratio depends on gain mismatch and phase mismatch. So if the image rejection is going to be very high, then the receiver is very good. And here they found that theoretically it falls well below 60 dB. So the image rejection ratio IRR is falling well below 60 dB. So which means that the gain variation must be less than 0.1 for an IRR of 60 dB. So the gain variation should be very less, or I can say the gain should be almost constant, which is a very, very difficult task in receivers. So maintaining the gain is going to be a very, very difficult task. So that is going to have a serious impact on the image rejection ratio. That's why we have seen that when you work at high IRR rates, you have to calibrate your Hartley and Weaver architectures. That's what we have seen. So they will conventionally work for low IRR only, but if your circuit demands a very high image rejection ratio, then you have to calibrate your system to overcome all these noises. So this is all about receivers. So we have seen so many architecture of receivers. I again say logically remember things. Need not by heart anything. Equations to some extent, if possible, remember logically. Otherwise, your own explanation can easily summarize the performance of each of the receiver circuits. And we focus a lot on receivers because they are very crucial part, because once the signal is sent, the transmitter role is over, but receiver must be a very perfect condition to receive your signal, and it has to filter it out from noise. It has to eliminate images, and so that is going to be a tedious process. So we have seen exhaustive study of the